At 1,000 hours local time, the U.S. destroyer Chung Hoon commenced its routine transit through the Taiwan Strait, accompanied by the Canadian frigate HMCS Montreal. This operation, conducted in international waters, is a standard procedure that American warships have performed for decades without seeking Beijing's consent. However, just 30 nautical miles to the west, a Chinese destroyer had a different agenda. At 10:07, radar operators aboard the Chung Hoon observed the Chinese vessel accelerating from 15 knots to 28 knots, altering course to intercept. It was no longer merely shadowing. The Chinese ship was closing in with clear intent. Calculations predicted the closest approach would be under 2,000 yards. The sailors aboard the Chung Hoon swiftly moved to battle stations they had drilled thousands of times before. But this time, it was not a drill. By 10:12, the Chinese destroyer had closed to approximately 22 nautical miles, about 55 kilometers away. At its current speed, it would enter weapons employment range in less than 17 minutes. The tactical action officer aboard the Chung Hoon accessed the threat library to assess the capabilities of the approaching Chinese warship. Inside the vertical launch cells of the Chinese destroyer were the feared YJ-18 anti-ship cruise missiles, known in Chinese state media as the Carrier Annihilator. Western analysts regard the YJ-18 as China's most dangerous naval weapon. On paper, the missile was indeed formidable. The YJ-18 measures 8.22 meters in length and weighs 1,580 kilograms. Its attack profile involves 3 stages. First, a solid fuel booster launches the missile from its cell and accelerates it to cruise speed. Next, a turbojet sustainer propels the missile at Mach 0.8, skimming 5 to 7 meters above the sea surface, making it difficult to detect amid sea clutter on most radar systems. It maintains this low, quiet flight path for up to 180 kilometers, using inertial navigation corrected by Chinese Beidou satellites to home in on the target's predicted location. The missile's signature move occurs as it nears the target. The cruise stage drops away, and a second solid rocket motor ignites, accelerating the missile from Mach 0.8 to Mach 3 within 4 seconds. The missile's terminal altitude drops to just 3 meters above the waves, close enough to touch the whitecaps, and the supersonic warhead completes the final approach in under 50 seconds. Traveling at this speed, the 300-kilogram warhead delivers approximately 150 megajoules of impact energy, comparable to a car crashing into a wall at 600 miles per hour and exploding. The Chinese destroyer was equipped with 64 vertical launch cells, typically loaded with between 8 and 16 YJ-18 missiles. At the current range, every missile could reach the Chung Hoon in under a minute from launch command to impact. Chinese military doctrine refers to this tactic as saturation attack, launching enough missiles simultaneously that some inevitably penetrate the defender's shields. The math appears straightforward. If defenders can engage only 4 targets at once and attackers launch 8 missiles, 4 missiles will get through. However, at 10:15, as the Chinese destroyer continued to close in, the Chung Hoon's combat systems operators were not worried, but rather amused, because that math had critical flaws that would soon become Beijing's problem. At 10:18, the Chung Hoon's electronic warfare team reviewed the threat profile of the YJ-18's seeker head. Their findings explained why no one aboard the American destroyer was sweating. The missile's active radar seeker operates in the X-band frequency between 8 and 12 gigahertz. This information isn't classified, it's simply physics. And physics brings vulnerabilities no software update can fix. The X-band offers excellent resolution, allowing the seeker to pick out structures from sea clutter in the final seconds of attack. However, the short wavelength also forces the missile to broadcast its position continuously throughout its flight. Each radar pulse reveals the missile's exact location and approach angle. From the Chung Hoon's perspective, a YJ-18 in its terminal sprint is like a missile carrying a neon sign that reads, "Shoot me." Even better, the advanced SLQ-32 electronic warfare suite mounted on the Chung Hoon superstructure has been countering X-band seekers since 1979. Its coverage spans from 50 gigahertz down to 2 gigahertz, with the YJ-18's operating frequency right in the middle. The latest variants don't simply detect incoming emissions, they jam them, spoof them, and create false targets that can divert missiles entirely off course. If the Chinese tried to overpower the jamming by increasing their missile's radar emissions, the missile itself would become a beacon, guiding American interceptors directly to it. The YJ-18's terminal sprint also creates an unavoidable problem for Chinese engineers. Accelerating from Mach 0.8 to Mach 3 in just 4 seconds requires burning close to 200 kilograms of solid propellant, generating a significant thermal signature. This flare is visible on infrared sensors from dozens of kilometers away. The moment the second stage booster ignites, every IR sensor on the defending ship locks onto the missile's exact location. The stage separation further aids tracking. When the subsonic cruise body drops away and the supersonic warhead ignites, the missile's radar cross-section, velocity, and altitude all shift suddenly. This brief transition period, lasting approximately 1.5 seconds, makes it easier, not harder, to calculate an accurate tracking solution. The missile's claimed 10G terminal maneuvers are pre-programmed and executed according to a fixed guidance script. It doesn't respond dynamically to defensive fire or incoming countermeasures. The YJ-18 was designed to strike targets that don't shoot back, cooperative targets such as stationary barges or retired hulls without electronic warfare capabilities. By contrast, the Russian Club missile family, which the YJ-18 is based on, has never successfully engaged a target defended by the Aegis combat system in over 30 years of service across multiple navies. At 10:23, the Chinese destroyer closed to 18 nautical miles. Its captain likely believed he held decisive trump cards. The Chung Hoon's crew, however, knew those trump cards were nothing more than expensive noisemakers. By 10:27, the Chung Hoon's primary radar, the AN/SPY-1 system, was tracking the approaching destroyer with mechanical indifference. This powerful spy radar is a symbol of American naval dominance. It features 4 octagonal faces, each over 11 feet across, providing 360-degree coverage from the waterline to directly overhead. Each face contains 4,350 individual radiating elements, none of which move physically. Unlike traditional radars that mechanically rotate to scan the environment, the AN/SPY-1 electronically steers its beam by adjusting phase relationships among thousands of transmitters. This allows repositioning anywhere within the hemisphere in microseconds, eliminating scanning delays. As a result, a target detected at one bearing can be interrogated from another bearing before a rotating radar completes one revolution. At 10:31, the spy radar was simultaneously tracking the Chinese destroyer, 23 commercial freighters, and 14 aircraft within a 200-mile radius. Operating in the S-band frequency range, 3.1 to 3.5 GHz, the radar balances detection range with resolution, using wavelengths long enough to propagate efficiently over the sea while minimizing sea clutter. Its peak power output exceeds 6 megawatts, concentrated into beams capable of detecting high-altitude targets beyond 200 nautical miles. However, sea-skimming missiles like the YJ-18 are more challenging. Radar horizon limits detection to roughly 35 kilometers due to Earth's curvature, which applies to all radars regardless of power. The Aegis combat system aboard the Chung Hoon is designed not to rely solely on its own radar horizon. It integrates Cooperative Engagement Capability, CEC, a network linking every sensor in the battle space. An E-2D Hawkeye aircraft orbiting at 25,000 feet can detect sea-skimming threats beyond 200 nautical miles and relay targeting data back to the destroyer's fire control system. The Chung Hoon doesn't need to see incoming missiles itself. It can launch interceptors based on data from any networked platform. At 10:34, the weapons control system on board the Chung Hoon continuously computed the Chinese destroyer's position, velocity, heading, predicted missile release point, and optimal intercept geometry. 4 UIK-43 processors managed over 100 simultaneous tracks while calculating engagement solutions for the highest priority threats. The Chinese destroyer scored maximum threat value across nearly every parameter. It was closing fast, carried potential missile payloads, had active fire control radar, and was approaching rapidly. The Chung Hoon's Mach 41 vertical launch system housed 96 cells loaded with American countermeasures. SM-2 missiles for medium-range engagement, reliable workhorses that have defended American ships since the Cold War. SM-6 missiles offering extended reach capable of engaging targets beyond the ship's radar horizon using networked sensor data. And evolved Sea Sparrow missiles, ESSM, packed 4 per cell for rapid, close-in response. Each missile type could engage the Chinese ship before the YJ-18s finished their first stage boost. The fire control solution updated 15 times per second. If the Chinese captain opened his missile launch cells, the Chung Hoon would detect it before the hydraulic doors fully cycled open. Should the Chinese vessel illuminate the American destroyer with targeting radar, the spy radar would detect, classify, and generate a firing solution before the Chinese operator could complete the launch sequence. At 10:37, the Chinese destroyer closed to 14 nautical miles, 26 kilometers, within theoretical missile launch range. The Chinese ship was now in a position where its YJ-18 missiles could reach the Chung Hoon in under 45 seconds. But it had also entered the range where SM-6 interceptors could neutralize it in under 30 seconds. The Chinese captain was betting that the Americans would not fire first. While his assumption about American restraint was correct, he was wrong about everything else. The confidence aboard the Chung Hoon was not arrogance. It was based on data and extensive combat experience. Since October 2023, Arleigh Burke-class destroyers, of which the Chung Hoon is a member, had been engaged in high-intensity combat operations in the Red Sea. Iranian-backed Houthi militants launched a variety of attacks against commercial shipping and American warships, including anti-ship missiles, ballistic missiles, cruise missiles, and drone swarms designed to overwhelm defensive systems. The Aegis combat system intercepted every threat. Over an 18-month span, American destroyers conducted hundreds of successful missile intercepts. SM-6 missiles intercepted ballistic missiles during their terminal dive, often moving faster than the YJ-18 sprint phase. SM-2 missiles successfully engaged cruise missiles at medium range with hit probabilities that made Chinese test data seem overly optimistic. ESSMs took rapid reaction shots against sudden pop-up threats with very short warning times. The Phalanx close-in weapon system cleaned up any threats that penetrated outer layers of defense. The entire defensive concept worked as designed, with each system covering the gaps of the others. Within 48 hours of each engagement in the Red Sea, terabytes of combat data were transmitted to shore facilities and defense contractors. This data included radar tracks, engagement timelines, interceptor performance metrics, seeker behavior under jamming, and every detail was rigorously analyzed. Misses were dissected down to the millisecond, and lessons learned were incorporated into the next software update, distributed fleet-wide within weeks. The Aegis system grew smarter after every single missile flight. Although this particular encounter would precede some of those data-driven improvements, decades of combat experience dating back to the First Gulf War had already validated the concept. The Chinese had no equivalent feedback loop, then or now. Their missiles had never faced jamming from a modern SL-232 electronic warfare system. Their seekers had never attempted to track targets executing combat maneuvers. Their fire control systems had never operated against an Aegis-equipped ship actively shooting back. The YJ-18's claimed 96% hit probability stemmed from test ranges where targets didn't maneuver, didn't employ jamming, and offered no defensive fire. It was akin to claiming boxing championships by knocking out a mannequin. Chinese state media could trumpet those numbers endlessly, but American electronic warfare officers called them job security. At 10:41, the Chinese destroyer closed to 12 nautical miles, close enough that lookouts aboard the Chung Hoon could see its superstructure with binoculars. The HMCS Montreal's crew had cameras rolling, documenting the approach for what would become one of the most watched naval encounters of the decade. The Chinese destroyer captain was bringing test-range statistics into a combat-proven fight, and he was running out of room to pretend otherwise. At 10:52, the Chinese destroyer crossed inside 10 nautical miles. Through the bridge windows, the Chung Hoon's crew could see the bow wave of the approaching ship growing larger by the minute. The Canadian frigate Montreal held position astern, its crew continuing to document the unfolding encounter. Both destroyers mounted naval guns on their bows. At this range, the mathematics of missile combat began to collapse. Flight times compressed to mere seconds rather than minutes, shrinking reaction windows and favoring the shooter. If the situation escalated to kinetic combat, it would come down to a discipline navies had not seriously practiced since World War II. The Chung Hoon carried the Mark 45 Mod 4, a 5-inch gun that American ships have relied on since the Vietnam War. The Chinese destroyer mounted an HPJ-38, a 130mm weapon reverse-engineered from the Soviet AK-130. On paper, the Chinese gun seemed superior. It fired heavier 33-kilogram shells compared to the American 32-kilogram rounds, had a rate of fire up to 40 rounds per minute through a vertical autoloader, a longer 9.1-meter barrel pushing shells at 850 meters per second, and an engagement range of up to 30 kilometers against surface targets. Chinese military forums enthusiastically compared these specifications, seemingly confirming the HPJ-38's superiority in surface gunnery. However, these discussions neglected a critical factor: fire control. The HPJ-38 utilizes the ZPJ-1 director, a combined radar and electro-optical tracker mounted separately from the gun. Radar acquires the target, optics refine the tracking, and a fire control computer calculates a ballistic solution that accounts for target motion, wind, and barrel wear. After firing, the system waits to observe the round's impact. If shells miss, the crew manually adjusts based on observed splashes and tries again. This approach is essentially a World War II methodology with modern sensors. By contrast, the Mark 45 operates in a completely different realm. Mounted directly above its barrel is the Mark 5 velocimeter, a Doppler radar that measures the actual muzzle velocity of each round as it leaves the barrel. Not theoretical velocity from propellant tables, but the real velocity influenced by barrel wear, temperature, humidity, and other variables that change shot to shot. This velocity measurement feeds directly into the Mark A160 gun computer system. The computer compares the predicted trajectory against the measured initial conditions and adjusts the next shot before firing. After several rounds, the system calibrates itself to actual real-world performance. If rounds miss left, the computer knows. If they fall short, the computer knows. Accuracy improves with every shot fired. The integration goes even deeper. The SPY radar can track outgoing 5-inch projectiles, monitoring where shells actually fly versus where ballistic tables predicted. This data feeds back into the fire control loop. By the 10th round, the system has characterized actual ballistic performance under current conditions and walks subsequent shots onto the target automatically. The HPJ-38 fires faster and throws heavier shells, but loses track of them after they leave the barrel. The Mark 45 fires slower, but learns from every shot. In the time it takes the Chinese gun to empty a magazine and hope some rounds hit, the American gun has found the target and consistently put rounds on it. At 10:58, the Chinese destroyer closed to 8 nautical miles, 15 kilometers, well within gun range for both ships. The Chinese captain faced an unpalatable calculus. His YJ-18 missiles were compromised before launch. His radar couldn't pierce Aegis jamming. His fire control couldn't match American precision. Turning back would anger Beijing, but pressing on meant confronting overwhelming technological disadvantages. There was one last option, a tactic that negated every American technological advantage, closing the distance to a point where technology ceased to matter. At 11:12, the Chinese destroyer crossed inside 5 nautical miles, 9 kilometers, close enough that crew members on deck were visible through binoculars. At this range, both ships' close-in weapon systems, CIWS, became relevant. Last-ditch defenses designed to shred incoming missiles in the final seconds before impact. The Chinese destroyer mounted the Type 1130 CIWS, China's most advanced system, featuring 11 barrels of 30mm rotary cannon firing at 10,000 rounds per minute. It had 2 ammunition drums holding 1,280 rounds of tungsten core penetrators, enough metal to theoretically saturate a cone of airspace and obliterate anything entering it. The Chung Hoon mounted the Phalanx 1B, 6 barrels of 20mm Gatling cannon, firing at 4,500 rounds per minute, a lower rate of fire, smaller caliber, and lower volume compared to the Chinese system. By every visible metric, the Chinese Type 1130 appeared dominant. However, the unseen factors made those metrics irrelevant. The phalanx uses closed-loop spotting with two radar antennas working together. One tracks the incoming threat, the other tracks the outgoing stream of 20mm rounds. The system monitors its own bullets downrange, comparing actual trajectories against predicted intercept points. If bullets drift left, the mount corrects right. If rounds fall short, elevation adjusts. These corrections happen continuously during the firing burst. During each burst, the phalanx literally steers its fire based on where rounds actually travel, not on ballistic tables. The Type 1130 tracks the target, but does not track its own rounds. This is the difference between hoping and knowing. At engagement distances under 2,000 meters against targets moving faster than Mach 2, angular errors measured in fractions of a degree produce complete misses. A sea-skimming missile crosses the final kilometer in roughly 1.5 seconds. In that window, the Type 1130 fires 250 rounds along a predicted trajectory. If the prediction is off by half a degree, and predictions always have some error, every round misses behind the target. The phalanx fires 112 rounds in the same window. After the first 10-round burst, with only 0.13 seconds of flight time, the system knows exactly where those rounds went. The second burst adjusts fire. The third burst walks the rounds onto the target. Engagement data shows first hits typically occur by the third or fourth burst, all within 1 second of trigger pull. The phalanx does not predict and pray, it observes and corrects. Discussions about caliber sizes miss the point entirely. A 20mm tungsten penetrator traveling at 1,000 meters per second delivers enough energy to shred missile airframes, rupture fuel tanks, and detonate warheads. The Chinese destroyer's technological advantages evaporated in the face of the Chung Hoon's superior electronic warfare, fire control, and close-in weapon systems. The encounter illustrated the decisive edge American naval technology and tactics held over Chinese counterparts in modern naval warfare.